Greetings, this is Mrs. Bird from Gettysburg College Advancing Science. Today we're going to be talking about electricity, specifically static electricity. Every day in our life we generate static electricity somehow. Think of a few ways. Write them down on your worksheet. We're going to use this machine. It's called a Van de Graaff generator, and its job is to generate static electricity. Before we get started though, let's talk a little bit about the science behind static electricity. This is an atom. An atom used to be considered the smallest particle of any matter. And you want to think just how small is an atom? Well, an atom is, if we had 1 grain of sand, there would be 50 quintillion atoms in a grain of sand, approximately. And this is what a quintillion looks like. So it's pretty small. But even smaller than the atom are the particles that make up an atom. An atom is made up of 3 different particles. One is a proton, a neutron, and an electron. Each one of these subparticles has a charge, actually. A proton has a positive charge. And you can remember that because both positive and proton begin with a P. A neutron has no charge. Think about your car when you're driving in neutral. It's not going forward and it's not going backwards. It's neutral. And then finally, let's think about the electron. And that has a negative charge. Now those charges are important to us as we try and understand just how our Van de Graaff generator and static electricity work. So if you think about magnets, oftentimes we'll pick up a magnet and we'll push 2 magnets together. If you happen to have a north pole and a south pole together, they're going to attract. But if you have 2 south poles or 2 north poles together, they're going to do what's called repel. They're going to try to push away from each other. Think about those magnets, about the force that you can feel but you can't see. The same thing occurs when we are working with the Van de Graaff or with static electricity. The basics behind the Van de Graaff is that opposites will attract, a positive charge and a negative charge will attract. Think about your protons and your electrons. A proton has a positive charge, an electron has a negative charge. Now, if we have 2 of the same charges, let's say we have a proton and a proton, they're going to repel. They're going to want to get away from each other or avoid each other. Same for an electron and electron, 2 negative charges. This image represents a Van de Graaff generator. When you think about the Van de Graaff generator, simply think about a rubber balloon and maybe a wool sweater, and you'll have the basic idea of how it operates. This belt is similar to your balloon material, and it's going to roll around a roller, which also has a piece of wool in the interior of the machine. That then generates electrons. Those electrons, if you recall, they want to repel from each other, so they're going to look for a place to disperse to. And that's going to be the large silver dome of the Van de Graaff generator. Keep in mind, as we use this Van de Graaff generator, that all of these have the same charge. This is represented as electrons. It can also be protons too, but we'll represent them as electrons today. Electrons, they all have the same charge. They want to repel. Okay, now that you know the nuts and bolts of what static electricity is, let's go ahead and have some fun. First thing I'm going to show you, this is called the grounding ball. And the grounding ball is going to collect those static charges, in this case the electrons that cover this ball. Just how does a Van de Graaff generator work? Let's go through a little quick demo. So this grounding ball is attached to our Van de Graaff generator. Inside here is a balloon-like material. It's almost like a giant rubber band. And it's going to spin round and round. Think about when you rub that balloon across your wool sweater. It's the same thing. Inside the bottom here is a piece of wool and some metal prongs. Those metal prongs are what's going to help us collect those electrons. Now, that rubber band is going to fill this ball with electrons, because those electrons want to jump onto the metal prongs that then lead it to here. If you remember what we talked about, when we talked about like charges, do like charges want to attract or do they want to repel? If I have two electrons, do they want to attract to each other or repel? And if you said repel, you're correct. Think about those magnets, just like we talked about. Okay? Now, I'm going to turn this machine on, and we're going to cover this ball. The band's going to go round and round, and this ball will get covered with negative charges. Remember, those charges that are alike, they want to repel from each other. Let's see what happens. So you can't see anything right now, but electrons are covering that silver ball, and they are all close together. They want to get away from each other. And if I use the bar, you can hear them jumping. The closer I have the ball, the quicker the jumps go. The further away I hold the ball, the longer it takes to generate. And you can tell it's a little louder. Now I'm going to turn the light out so that you can actually see. Hopefully, I don't know if you can see, they look very closely. And the electrons don't take much force to jump this close. 1 inch is about 10,000 volts. That sounds like a lot. But in this situation, it's really not harmful. This is just like a carpet shock that you might, as you walk across and stab your little brother. That's what it's going to feel like. Now, the further away I move it, each inch is 10,000 volts. It's going to be a little bit stronger. Now let's listen. And I think you can see that lightning bolt structure. Takes longer to get there, but it's a broader, thicker bolt. Now I'm going to hold this grounding ball very loosely. I want you to watch what happens. Do you see that each time there's a jump or a bolt, that jolts the ball in my hand? I can feel it pushing away, just like we could feel two magnets pushing each other away, or repelling is the word. Okay, the further away I get, the more force that's going to have. If I put a candle here, that wave, that electron wave, will make the flame of the candle blow away from the Van de Graaff. A little closer. Now I can actually turn the speed of the belt up a little bit and get it to generate a little bit more electrons. Okay. Now I'm going to turn the machine off. And one thing I want you to notice is I'm not going to touch this ball until I've touched it with this grounding ball, because if I touch it, there's going to be lots of electrons. They want to repel, and they'll go to anything. They don't have to just go to this ball. If they go to my finger, I'm going to get the shock. So, there. Sometimes, after a while, it'll just discharge anyway, because the air can actually conduct those electrons away. But, if I didn't have my grounding ball, I've actually seen people use their finger as the grounding ball. You get lots of shocks. I don't like to do that. Instead, this grounding ball collects the electrons from here. Remember, you're covered with the same charge. They want to repel. They want to get away from each other. They're going to jump onto this ball, any source at all. If it happened to be my computer closer than that ball, it would go right to my computer, or my finger, or whatever's nearby. So that's why I like to keep this grounding ball relatively close to it, because I don't want it to be my finger that gets the shock. I'd rather it get the grounding ball. Okay, so we saw that those electrons covered it. We know that like charges want to repel from each other. Opposites attract, okay? Like charges will repel. North pole on our magnets. Now let's try something else. See if you can come up with what's really going on here. I just have some pie plates. Regular pie plates. Nothing magical about them. I'm going to put one on here. If this ball gets covered with negative charges, what are those negative charges called? Electrons. What's that plate going to get covered with? Electrons. How about this one? Electrons. Electrons. So all of these plates are going to get covered with electrons. Let's go ahead and put them all on. Hopefully these plates will cooperate. Sometimes if I have the wrong plate on there, it doesn't work. But let's see. Let's turn our light back on. So, nothing magical here. Maybe if I said abracadabra, though, we might be able to convince you that this is magic. Is it magic? No. It's just science. This ball is going to get covered with electrons. Each plate is going to get covered with electrons. Let's see what happens. Go ahead and make a prediction for me. What's going to happen when I turn the Van de Graaff generator on? This gets covered with electrons, and each one of those plates gets covered with electrons. What's your hypothesis? Okay, let's see what happens. Okay, if I had said abracadabra, you might have thought it was magic, but it's not. It's just science. Let's go ahead and turn that off again, and you can see I can touch that ball now because all of my electrons have been taken into my grounding ball, taken down into the ground, just like the grounding ball name is. Okay, so that was pretty cool. I like to do that because it shows that each one of these got covered with electrons and then wanted to repel from each other. Now, let's move on to the next one. Let's hook this back up. I have another wand here, and at the end of this wand is just it's just a ping pong ball basically, okay? It's silver, looks pretty fancy, but it's not. It's just basically a spray painted ping pong ball. When I take and push it against it, you'll see that it just acts just like a ping pong ball would do. It's going to bounce off, okay? Nothing special. It's just going to hang there. But when I turn on this Van de Graaff, I'm going to end up covering this ball with electrons, right? Those negative charges. What do those negative charges want to do? They want to repel. They want to get away from each other. So there's going to be a couple things going on here when we look at this part of the activity. One is going to happen right away, very quickly. The other is going to be for a while. But I want you to be very observant and see if you can catch what happens right away. Okay? I'm going to turn the machine on again, and we'll see what happens. So, see, this is it without the machine on. Just kind of bounces there just like a ping pong ball would. Now, I'm going to turn on the machine. Watch that very first thing that happens. Oh, okay. Did you see that? It happened already. It attracted in, okay? Think about it. Why did it attract in? Now, if you keep an eye on the wand, I am not moving that wand. But the ball is moving. I know you can't see the top of the wand in this video, but look at my hand. I am not moving that. That is pretty cool. So what do you think's causing that? What is causing? Let's go ahead. We'll discharge it for a minute and talk about that. So what happened in the very beginning? This ball attracted to our dome. Okay? So maybe this ball actually had a positive charge, and our larger dome had a negative charge. Those are opposite charges. What do they want to do? They want to attract. Okay? Then, this ball, once it came in contact with the larger dome, what did this ball get covered with? This ball's covered with electrons. This ball touches it. What did this ball get covered with? If you said electrons, you're correct. Okay? So, we have electrons. We have electrons on here. What do the same charges want to do? They want to repel. Let's take a look at it again. See if you can watch for that first time when it goes in and is attracted. So here it is. Same thing. Nothing special, just a ping pong ball. bang it against a metal ball. Okay? I'm going to turn it on. Watch quickly. It happens very quickly. And then you're going to see that repulsion happen. Okay? There was the attraction. Whoop. Not working so well there. Let's try it again. All right. I'm not generating any charge. Okay, let's take a look one more time. I'm going to watch it go in. The small ball then picks up all of the electrons. Both the large ball and the small ball have electrons on them. What are they going to want to do? They're going to want to repel. So keep your eye on. Let's turn it on. There it went in. Okay, so now, took a few seconds, a few hits, but both balls are now covered with electrons. And you can see, kind of like an orbit around planets, right? Okay? They're both covered with electrons. They want to repel. But fortunately, that ball is attached to the wand with a small string. Okay? Now, so then, again, I can touch the ball with no problem. Our next one that we're going to look at is actually using this fluorescent light bulb. It's just the same as any fluorescent bulb that you might find in your school building. Okay? It's nothing special. This is called not an incandescent bulb, a fluorescent tube. And inside these are molecules. When those molecules get excited, they start to move around. And when they bump into each other, they generate light. Yeah, you guessed it. And we're going to watch it. This tube is going to light up because energy from these electrons are going to be transferred to this tube. Now there's a couple things I want you to watch for. I'm going to turn the light out, and I want you to watch for what happens when I'm holding the tube next to that bulb. I'm not going to touch the dome. I'm sorry. When I'm holding it next to the dome, I'm not going to touch that dome. Instead, I'm going to hold it just a little bit away from it and see if you can see something in particular, some special thing that's happening that is different than you might expect. Okay? Remember, this is filled with gas molecules. When they move around and get excited and bump into each other, they're going to generate a light source. So keep an eye on that. Now also, at the end of this part of the experiment, I get shocked every time. See if you can see what happens each time I get shocked. I don't like to get shocked, but keep an eye on the tube and see if you can see what happens. Okay? Give me a moment to get set up. I'm going to turn the light out. We'll turn the generator on. One other thing I forgot to show you is I'm actually going to stand on this stool. This is an insulator. What does an insulator do when we're talking about electrons? If you said that it stops electricity from moving or electrons from moving, you're absolutely right. So this insulator or stool is made out of rubber. And I have on tennis shoes today, also made out of rubber because they are insulators. What's going to happen to those electrons when they hit that insulator? Are they going to be able to keep on moving through? Are they going to have a passageway through? Are they going to be stopped? If you said stopped, you're correct. An insulator prevents the flow of electrons or electricity, and that's what's going to help us to see this light glow, because the electrons are going to be stuck on me. And sometimes when I do this, my hair actually stands up because my hair is covered with the electrons also. So keep an eye on that. Remember that I'm standing on the insulator. Does anyone know the opposite of an insulator? What is it that allows electricity to move through it easily? Think about wires. The metal part of wires. Those are called conductors. Okay? So a conductor allows electricity or electrons to move through it easily. Let's see what happens when we turn on this light. Okay, my lights are out. I'm going to stand on my insulator. Now, I'm going to try not to shock myself. That happens every time. And hopefully, I don't know if you could see it. I might have to move to the other side just so I can show you how that works. for now. Okay. Okay, now I have a styrofoam cup. Okay, and inside that styrofoam cup are styrofoam peanuts. I want you to make a hypothesis. What do you think is going to happen? I'm going to put this on the top here. I'll turn the Van de Graaff on. And what do you think will happen? Take a minute, think about it, make your hypothesis, and then we'll see what happens. Okay, everybody ready? Okay, hopefully you could see that those styrofoam peanuts flew out of the container. It's nothing that I did. It was all the electrons. Each one of the cup was covered with electrons. Each one of those styrofoam peanuts inside the cup then got covered with electrons. And they wanted to escape. They weren't attached to each other, so that's exactly what they did. Now let's try it with another cup, one that you can see through. I'm going to adjust my camera just a bit. Keep your eye on it, okay? It takes a few moments for the electron charge to build up, but you'll be able to see it a little better in that cup. There we go. Okay, believe it or not, some people do that with Rice Krispies. Can you imagine the mess that would make? But the same process is going to happen. Each one of those Rice Krispies gets covered with electrons. Like charges want to, say it, repel. They want to repel. Same or opposite charges, they want to attract. Okay, one more. I have one more demo I'd like to show you. And I wish that I had each of you here so that I could have you be part of my experiment here. But instead, I want you to imagine that this maybe is your hair. Okay, and I'm going to put this on the Van de Graaff. It's just yarn and a ribbon. Let's see what happens. What do you think? By now, I think you guys have an idea what's going to happen. Tell me why it's going to happen. I'm just going to tape those threads down. Let me turn the light back on. Okay, so those threads are taped down. Let's see what happens. Any guesses? There we go. Any hypotheses? So our white ribbon's starting up. So imagine if this was your teacher's hair. It's always the best part of the day. What's happening here? Each one of those strands is covered with electrons. They all have what charge do electrons have? They all have a negative charge. They all have the same charge. What do they want to do? They want to repel. Now let's see if we can play around with it a little bit. When I collect those electrons using my grounding ball, they don't stand up anymore. Flat as a pancake. But let's go ahead and let those electrons build up again. And there we have it. This is what would be happening to your hair. You were here right now with your hand on the globe. And I can attract them. This ball has a positive charge, so those negative charges are attracted to this positive charge grounding ball. Okay? So, let's make a quick wrap up here of what we did. If you recall, our first part of the experiment were these pie plates, and that demonstrated what to you? The dome was covered with electrons, and each pie plate was covered with electrons, and what happened to those pie plates? It starts with an R. They wanted to repel, okay? Repel means just get away from each other, and they flew away from each other. And we pretty much did a number of experiments with the same exact way. This shape, this ball, little ball, it attracted at first, covered itself with electrons. Both balls are covered with electrons. They want to repel. Another example of like charges wanting to repel or get away from each other. Okay, now a quick review of what makes all this work. Give me the 3 parts of an atom. What's one part? If you said electron, correct. If you said proton, correct. If you said neutron, correct. Do you remember which 2 are in the nucleus of this structure? What is that structure? I guess we should say that first. What's the structure that has an electron, a proton, and a neutron? It's called an 4-letter word and an atom. A-T-O-M. And that atom has 3 particles, electron, neutron, proton. 2 of them are in the nucleus. Anybody remember which 2? It's going to be your proton and neutron. Of those 3 particles, which one, think back to the picture we had of our atom, which one do you think can travel around the easiest? Which one can jump from atom to atom easiest? The electron. Yeah, it's in orbit. It's not in that nucleus. So today we had some fun with static electricity. I want you to remember, though, we were playing with static electricity. We were doing science with static electricity, not magic. I don't want you to think that you should be able to play with the electricity that comes out of an outlet, because that is direct current, meaning it goes through you. This is, I like to call it lazy electricity. It goes over you. Every time I was, when I was holding that glass rod, I could feel the electrodes going over me. It wasn't going through me, and it wasn't damaging any parts of my body. So don't play around with electricity, but in your daily life, I want you to think about, that's static electricity, or there's static electricity. What's happening here? When you have 2 different materials rubbing against each other, that's usually when you're going to get static electricity generated. Okay? Have a great day, and thanks for visiting. This is Mrs. Bird from Advancing Science at Gettysburg College. Okay, let's go ahead and turn the generator on, and I want you to keep an eye and see if you can see those sparks that are happening. Okay, so you can see I'm moving my hand back and forth across this glass bulb. What do you notice that's happening? Hopefully some of you are noticing that it's only going to my hand. The part of the bulb below my hand is not getting lit up. Now I'm going to turn the Van de Graff off, and this is where I usually get my shock. So let's see if I can do this. Did you notice when I got the shock? Let me go turn the lights on. So first, let's take a look. If you noticed, the light was only generated up to my hand. This part would stay dark. If I move my hand here, this much was dark. If I move my hand here, this whole part was dark. And that's because electrons are lazy. I call static electricity the lazy electricity. It goes over me, okay? I could feel as soon as I put this bulb up to the Van de Graaff, I could feel the electrons moving over me. Small hairs on my hand and a little bit on my head started to stand up and repel.